Now that we've talked about magnetic forces and magnetic fields, we can move on to electromagnetic induction, which is an important one because essentially it's how we develop all of our electricity. Unless you're talking about a battery or a solar cell, this is how we power all of our electrical devices. So what electromagnetic induction says, or what we've found, is that you can create current. Now current is amps, I, EMF is voltage or V. So I realize that this statement seems to kind of contradict, but basically to have current, you must have some kind of an EMF, some kind of an energy source to push the charges. So we can create this in a wire by simply changing the magnetic flux that is near it. So basically what we look at is the rate of flux change will tell us how much induction we have. So as a reminder, we're going to take a look at flux. So we have our symbol here for flux. That's the capital letter phi. So we're talking about magnetic flux, hence the B. We have our integration of B dot dA. So just like with Gauss's law, remember that the area vector points perpendicular to the surface. We have to have our B arrow and our A arrow have some commonality in terms of pointing in the same direction. We know that to be a dot product. If the vectors are aligned tail to tail, that's a cosine function. Now, last chapter we learned that Gauss's law for magnetism didn't offer much because it was always zero. This is not Gauss's law because we're not using a closed surface with that little symbol. We're not doing that. So this is not a zero type equation. So if we scroll down a little bit, what we're going to be looking at is something known as Faraday's law. Faraday's law says that our EMF, the script E, is going to be equal to the rate, I've got the derivative with respect to time, the rate of change in our flux. Now the negative sign is there just as a direction so we can figure out which way the current's going to actually flow, but this right here is our equation. Now I can put an N in front because if I look at the flux through a particular section of wire, well, if I have that wire coiled, every coil will have that same EMF in it, and it builds, which is why we commonly see big coils of wire when it comes to things involving electricity, whether it's an electromagnet, which was a couple chapters ago, or whether it's this. Now, sliding over here, we have Lenz's law. Lenz's law says that the induced current produces, the induced current direction. So when we have this happen and we get current, that current is going to have its own magnetic field. We can figure out the direction using the first right-hand rule. We did that during 2 chapters ago. So that current that gets made, it gets produced, has its own magnetic field, and that magnetic field interacts with the original magnetic field, and they actually oppose each other in terms of the cause of the change in flux. So we'll see some examples, but if I'm moving something to the right and it's causing a change of flux and that's giving me a current, the current is going to actually push back to the left and it's going to oppose that change. So basically this is showing us that we can't just use some gravitational energy and get something set in motion and get all this free energy. It doesn't work that way. And there's some good demonstrations that I'll try to find on YouTube, since I can't do them in front of you, to kind of give you some examples. So if we scroll down, to change the flux, what can you do? Well, you can change the strength of your field, you can change the size of your area, or you can change the angle between them. So that would be, that our method for changing the flux, which is how many magnetic field arrows are going through a particular area. Now, if we reverse the magnetic field direction, what you're technically doing is changing the angle, but that is also a possibility. How is it that you could change the direction of your magnetic field? just by doing a quick switch of connections or a quick switch of current or a quick switch of whatever. So over here, first right-hand rule. If we take a look, we've got our finger curl. First right-hand rules always involve finger curl and a thumb. That's it, just two parts. So our thumb is going to be the direction that you decide is the positive area direction. Remember, area is a vector coming out of our surface. So if we come down here, I have this green arrow pointing up. So clearly I have defined this loop right here is going to be in the, what is that, the XZ plane with the Y or J hat plane going straight up. So this area vector is J hat, positive J hat. So if I take my right thumb, and you should be doing this literally with your hand right now, right thumb pointing up, my finger curl is going in this black arrow direction. It goes in towards the screen, around the back, out towards the front of the screen, so I get this rotation. That's going to be our definition for positive direction. And so if we look down here, using the equation, remember there's a negative sign out front, that's just for direction purposes. So if I increase my flux, maybe I'm increasing my magnetic field strength perhaps. So if I increase my magnetic field strength, I'm getting an increase in flux. So the rate of change in flux right here is a positive. But there's a negative out here. So what does that mean? It means that our current is going to be going in the negative direction. Our finger curl simply defines what positive direction is. So if we increase our flux, we're going to get an arrow, a blue arrow, going in the other direction, because that's what our equation tells us, that we are going to end up with all this together, negative current. If we come over here, I still have the same positive direction for current. I still have my A pointing up. If I decrease the flux, and I can do that a number of ways, let's just say for simplicity that I'm just making B smaller. If I decrease the flux, what do I get? I get a negative rate change. I still have a negative out front, gives me positive. So I see that two separate opposite actions, increasing flux, decreasing flux, produces current that goes one way and then another. And what we're going to find is that setting up a device that increases and decreases the flux back and forth and back and forth and back and forth is going to be the by far most convenient way for us to do this, to change the flux, is to reverse it back and forth. And so what does that do? It means your current goes one way, then another, back, forth, back, forth, back, forth. And what does our current do? Our current alternates. AC, alternating current. Until now, we have been dealing strictly with DC, direct current coming from a battery. A battery just drives the charge forward, 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 forward. Alternating current is going to come from anything that has rotation to it, and it causes a back and forth, back and forth, back and forth motion. So our charges are literally vibrating in unison back and forth. So that's how we do Faraday's law with our little rate change for flux function. So it's actually a pretty simple little equation there. So if I scroll back up, just a reminder to ourselves that our flux is going to be the integration of B dot dA. So we are going to use that, and then once we can figure out what that is, we can plug that in here and see how it changes. So what we're going to do is look at the change in our strength, the change in our size, the change in our angle. So this right here, motional EMF. So if I take this random conducting rod in the presence of an inward facing, red X's, inward facing magnetic field, if I simply just move this to the right, we talk about positive charge motion. So third right hand rule, I want to look at the force felt by all the positive charges in this rod. So right hand rule, fingertips going straight into my screen. Thumb is going to the right. Our palm is facing the top of the screen. So that means that all the positives get pushed up. You could look at negatives. They're going to it's the same right-hand rule, but a negative means opposite. Negatives get pushed down, positives get pushed up. Just by moving this metal across, you actually get a positive buildup and a negative buildup. And so what we can do over here is we can find what that EMF is going to be. We can figure out what that difference is between location A and location B. Remember, voltage is always technically a change. So we can compare the difference between those two locations. Electric field multiplied by the length is the equation. And if we look at this right here, as we move our particle to the right, eventually we end up with no more particles moving. You're not going to get every single positive built up there, because the fourth positive that tries to go up there is going to be repelled back away by these three. So we're going to eventually reach an equilibrium point. At that point, these two forces are going to be equal, and just like our velocity selector from a couple chapters ago, we can figure out what the velocity is here by doing E over B. And what I can do is multiply B over, and so I can figure out right here, I can figure out what the potential difference will be between the ends by simply taking the speed at which I move this thing, how strong is the magnetic field, and how long is our piece of metal. Now that doesn't do anything for us, right? I mean, it's moving along, the charges shift, and as soon as I stop, the charges unshift and go right back to where they were. But what happens if I could connect this to a conductor? I slide down a slide wire generator right here is that same concept. I have this rod moving to the right. I get a buildup of positive, a buildup of negative. They don't shift down because there's a magnetic force driving them forward. But what can happen is this black wire is stationary. This whole thing is stationary. So what can happen? Since the positives can't move down onto the negative end because of the magnetic force, they can follow here, 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 and back. And once a positive gets there and a positive leaves there, another positive can go up. So this rod behaves just like a battery. So this isn't the alternating back and forth type of current. This is literally all of our current going in one direction. Now what happens if I stop my hand here, if I'm moving this with my hand, and what happens if I move it back to the left? Well, if I move it back to the left, now my positives build up down here, and the current will go the other way. So if I vibrated my hand back and forth this slide wire generator, I'd get alternating current. Now, in looking at this, we can see which direction our current's going to be. Let's see if it makes sense using Faraday's law. Faraday's law says that we have our EMF is going to equal negative rate change. So basically, are we increasing or decreasing the flux? Which direction is our area? And let's use the equation. So first, looking at the flux. My B never changes. It's constant. The angle between the area is right here, traced out as this square / rectangle. So our area orientation stays the same, so the angle stays the same. So if B doesn't change and the angle doesn't change, what is going to change? Well, as I slide this, and let's see if this is all connected together. This might be a disaster. As I slide, oh no, it's good. As I slide this over, I haven't changed the strength of my magnetic field. What have I just done? I have changed the area. I have enclosed more arrows. You might say, yeah, but this field isn't any stronger. It doesn't matter. Flux is how many field lines are going through an area. If I make the area bigger, more field lines. So in doing this motion, what we have done is we have increased the area. So if I increase the area, my flux is going to increase. So my flux is increasing. I get a positive rate change. Now, I want to do my first right-hand rule. My field points into the page. I want my area to point into the page also because it's a dot product. So if they point together, I get a nice simple positive dot product. So literally take your right hand, point your thumb into the screen, and your finger curl is very clearly going in the clockwise direction. This is clockwise. Our current is going in the other direction, so we end up with negative current. Well, let's see if that makes sense. The equation is negative change in flux. I have a positive change in flux, a negative sign in front of that. We should end up with negative current, and it makes sense. And I intentionally did not slide down to show this, so we could do it all through discussion, but there it is. And we can actually figure out what that value is because we have our VLB. We figure that out from further up. But again, here it is. We have a change in area. So you notice rate change of flux. B is a constant. Bring it out front. Negative is still there. So all we're doing is we're looking at the rate change of our area. Area is going to be length times whatever change in horizontal location we have, and there is your velocity. So we actually get the same equation. Now, Lenz's law. We mentioned it. We didn't prove it. Lenz's law. So moving up here, I move this thing to the right. It causes current to flow up through it. Figure out what the force is on the blue current. Third right-hand rule. Fingertips are the red, so fingertips point right into the screen. Thumb is our current. That blue current is going straight up. So fingertips in, thumb up. And if you're using the right hand, your palm is pointing to the left. So if I move this rod to the right, it is going to experience a magnetic force pointing back to the left. I encounter resistance beyond just friction. I get resistance pushing back on my motion, causing the charge flow. So the upward current through the rod is pushed to the left. That is Lenz's law. So if I just gave this thing a shove, if I made sure these rails were very, very low on friction, and I gave this thing just a shove, I can't expect it to just keep on coasting and coasting and coasting because there's going to be an additional force that develops slowing it down. It's almost like an air resistance kind of a thing, a terminal velocity kind of a thing. So that's Lenz's law. So this is a slide wire generator, and it's not something that we typically have a lot of use for, but it is something that can produce electricity. Why don't we have use for it? Because once you move your hand this way, or you move it this way, it's done. Now you can move it back the other way and reverse the current and then go back this way. So you could do that. The only problem is that there's a much more efficient way to get your back and forth repetitive motion than to move a wire back and forth and back and forth. Right? And that's going to be using some kind of a loop. So here, my attempt at a three-dimensional drawing, I've got some kind of a natural magnet. So I've got my north pointing up, and I suppose we could use an electromagnet, a separate set of wires, a separate set of coils. We could set up an electromagnet, but it's common to use just a natural magnet. I've got my magnetic field points where a north needle would point, and it would repel away from a north, which is why my arrows point up. And I've got my wire bent into it looks obviously kind of square or rectangular. It could be a circle, it doesn't matter. Drawing it out as a rectangle is actually kind of simple at the very beginning. And so if I look at my side view, there is my magnet, the red magnetic field, and this right here represents my loop in that field. And I'm going to start simple. I'm going to start it with an orientation that has the area pointing straight to the top in the direction of our magnetic field. So, so that's what we have right there. Now, I have just wires. There's no current going through the wires. It's just sitting here. The current that we're going to get is going to be induced, so I don't have this connected to a battery or anything else. Rotation is going to be caused by an external mechanical force. So basically, I'm going to spin this thing around in a circle, and that circle is follow my cursor. That circle is going to be going around like this. So let's see how I did here. Nope, they're not grouped together. So these things are going to spin around in a counterclockwise circle. Now, when we do that, it's got to be some external mechanical force. So this could be water flowing through a dam, pushing it, spinning it. This could be wind pushing it, spinning it with a turbine, or it could be your natural gas, oil, coal, nuclear plant that just boils water and shoots steam past the turbine. This is the turbine that's going to spin around in a circle while the magnet stays where it is. So I'm going to get upward red arrows for magnetic field the whole time. I got a reminder that my flux is B dot A. Right now I have the orientation between them as 0 degrees, so I have maximum flux right now. So basically what I notice is that as soon as I start to rotate, I'm going to get a decrease in flux, no matter what, from this particular position. Now, right here, first right hand rule. My thumb is pointing with the green arrow. My finger curl goes in on the right, out on the left. So this picture is not the current that I have currently. That is just a picture showing me the definition of positive current. So if I calculate positive current, my current's going to flow like this. If I calculate negative current, it's going to be X here and a dot there. So what we're going to do is we're going to start the rotation. Here we go. There it is. So we have rotated this thing slightly to our left, counterclockwise. We have just changed the angle. We said that at A, we are maxed out, so which means we have to have a decrease. So we have a decrease in our flux because our angle is increasing. So I get a negative rate change in my flux. I have a negative sign out front. I get positive current. So that means, if I scroll up just enough, that X was over here, so right there, I've got an X there, and I've got a dot there. You know, in hindsight, I should have color-coded these things so you could see the difference here, but we'll see as we go through. We got picture after picture, we'll be all right. Now, I get to right here. I have orientation perfectly perpendicular between my two arrows. Flux is 0, but the rate change is not 0. We are still going through a change, so do not be confused between flux being 0 and your change being 0. We just went from some smaller positive value down to 0. That's still a negative change. Still a negative sign out front. Still positive current, so I still have my X here and my dot here. And instead of making this particular slide, you know, too long so it doesn't fit on a piece of paper, we're just going to go to the next. So this is C right here, so we've got our area pointing straight to the left. Continue rotating, so that mechanical external force is continuing to push. So now I have arrows that are opposing each other. I am approaching anti-parallel, so I now have a negative flux. Going from 0 flux in C to a negative flux is still a negative change. So my magnitude is increasing, but because it's a dot product, I actually end up with negative flux. So I still have a negative rate of change. So I still have positive current. And if I complete 1/2 of a rotation, I get to this point right here. I am now at a maximum amount of negative flux. So I went from C, which was 0 flux, to D, which was a little bit of negative flux, to E, which is our maximum negative flux. I have just maxed out my negative amount of flux. I can't get any more negative flux than I have right there. So that entire half of a rotation, we had a negative rate change the entire time, negative sign out front, positive current. So from A to E, the entire first half of a rotation, we had non-stop positive current. And remember, our positive current would mean that the X was over here based on where our area is pointing. And again, do it right now. Take your right hand, point your thumb down with the green arrow. Your fingertips are going in on the left-hand side. So that's where our X is. So you could follow where that X is in that particular wire. It's always pointing in the same segment of wire. Now, we don't stop there. Now we continue rotating with our, again, our external mechanical force. We get to F. Now I don't need to go through every 45 degrees, I think. I think we can now see what's going to happen. So as I continue rotating counterclockwise, I have maximum negative flux, and that flux has changed to 0. While the magnitude is decreasing, I am going from a negative value to a 0 value. That is a positive change. From F to G, I'm going from 0 to positive. So all the way from E to F and then to G, and G is right back to where we started with segment A. E to F to G, I'm going from negative to 0 to positive. That entire change is a positive rate of change. So going from negative to 0 to positive, I end up with a positive rate change, negative sign, negative current. So half the turn is a positive current, and then half the turn is a negative current. And if I get this thing spinning and spinning and spinning and spinning, whether it's a hamster on a wheel or whether it's wind driving a turbine, I get alternating current. It alternates every half of a turn. I could graph these things with each other. If blue is my flux, I have maximum amount of flux when I have my arrows perfectly parallel or anti-parallel, in this case parallel, positive dot product. At that particular moment, it's just like throwing a baseball into the air and it reaches a high point. At the high point, what is its velocity? 0. And then it starts coming back down. Same thing there. When I get to that maximum amount of flux, I went from a positive change to a negative change. I stop for just a second. So for that split second, I have 0 EMF. And then as my flux decreases because of the orientation, and it becomes 0, and then it becomes even more negative, that entire time I have a change. And what happens? Our EMF goes up and goes down. And what you'll find is that if you take the derivative of this blue line, 0 slope, 0 value. Maximum slope, maximum value. Down here, 0 slope again, 0 value. Red is the derivative of the blue function. And right here, that's exactly what we're looking at. There's my blue function. Take the derivative and you get the red line. And we got that negative slope as well. So as I have a negative change, right there, there's a negative slope, I get a positive EMF. So there's a graph that shows the relationship between the two of them. And remember, we can't just get it going and it goes on forever. We have Lenz's law slowing things down all the time, which means we have to continually push to get this thing to rotate. So Mr. Bondi's got his little Nissan Leaf, and so I'm always asking him about his electric car. So when it comes to an electric car, you've got some battery source, you've got there's some electric source, you got your electric motor, it spins the wheels. So when you push on the accelerator, you can't call it a gas pedal now, when you push on the accelerator, you are telling the car exactly how fast to go. Most of us are used to driving a gasoline-powered car. And so you get to a particular speed, and then you just kind of keep your foot just in that perfect spot. And as you take the foot off the gas pedal, your car still can have a decent amount of coast. And so you get used to driving your gasoline-powered car. You don't want to stay on the gas and then all of a sudden slam on the brakes. So when you see a red light way up there, you take your foot off of the gas and you let your car just gradually slow down. And either the light turns green, you can continue that momentum forward, or you can gradually apply your brake. For an electric vehicle, it doesn't work that way. As soon as you take your foot off the gas pedal, you're telling the car, I don't want to go forward anymore. And what happens is that the electric motor, an electric motor is current flowing through with a battery near it. As soon as that motor isn't being used to drive the wheel forward, as soon as you do that, it becomes an electric generator. You have a mechanical force spinning a magnet and wire past each other, and so what happens is for your electric vehicles, you have this thing called regenerative braking. Basically, when you take your foot off of the accelerator, your wheel spins and puts energy and charge back into your battery. Now, it's not, it's not like you can just do this and you have energy forever. There are going to be limits. One of the big things is that your charging rate is going to be less than the discharge rate of the battery. Your battery driving the wheel forward has to go against air resistance and friction and all those sorts of things, whereas when I do my regenerative braking, I'm not going to be getting as much back. I'm not going to recoup all of that. So you can't just drive it forever and ever and ever. Simply because you're driving more than you're braking. You might drive for 4 miles and then brake once, kind of a thing. So anyway, that's an interesting thing. So one of these days I'm going to ask Mr. Bondi if I can drive his car, because the first thing I asked him was, hey, so when you drive and you come to the light, I mean, how noticeable is it? And Mr. Bondi said that as long as he doesn't have to slam on the brakes for a sudden red light, he said he can drive his way home, which is, let's see, I'm like 12 miles away and he's like 3 miles past me. So in his 15 or 16 miles of driving home, he says he can get through without touching his brake. He can, as long as he doesn't have to slam on the brakes, which is kind of cool when you think about it. This one right here, I'll find a video for a magnet through a tube. Some of you saw this last year in physics when I was just kind of going through and doing some fun demonstrations. This is a copper tube. What is a copper tube? An infinite number of little wire rings, wire loops, stacked on top of each other. This is a magnet that produces its own magnetic field. So out of the north into the south, complete loop. So these red lines represent our magnetic field from the magnet inside as it falls down. As we scroll down, so here is one single loop of that continuous copper tube. And so what happens is this thing falling down is no different than the ring moving up past the magnet. So I'm going to look at the ring moving up. I am going to look here, so as my magnet comes in, I know that I have an arrow coming, pointing here. See this red arrow? If I scooch up a little bit, below the magnet, my magnetic field comes in through the copper tubing, and above the magnet it goes out of the copper tubing. So the red arrow represents the magnetic field caused by this south. So if I visualize the loop moving up, what I find is that the red arrow is going to get stronger and stronger and stronger because it's getting closer, right? So as it gets stronger and stronger and stronger, I get a change in flux, an increase in my flux. And what's going to happen is we're going to get this current that is going to be induced. The induced current, as it goes around, and you can do your right hand rule to figure it out, as it goes around, what's going to happen is it's going to have its own induced magnetic field that I've drawn in green. First right hand rule to figure out the magnetic field direction around a wire, right here. Point your right thumb towards your face. Your finger curl goes up and around. So I end up with a magnetic field that has a south pointing this way. I have a south here, and I have my arrow pointing down like this. If I have a green magnetic field that looks like this, look at the red magnetic field and see how it points. If I have a north up and a south down, my magnetic field points like this, with my arrow coming in the bottom and going up to the top. Well, here I have in through the top and down through the bottom. What does that mean? It means that this green magnetic field is behaving as if I had a magnet that was south up and north down. What would two souths do? They would oppose each other. When this thing falls through, it reaches a terminal velocity and it seems to just slowly float down instead of accelerating at 9.81. Once it gets past and our flux begins to decrease, the current swings around. If the current swings around, then my green field swings around. which means my north-south orientation of this imaginary magnet swings around. And now I have a north and a south. What do a north and a south do? They attract each other. So I get this pull up and I get this push up, causing my magnet in either scenario to reach a terminal velocity and just slowly float downward. And again, I'll find some videos on YouTube to post. So here's Faraday's law showing how our current will develop, negative versus positive. So first, right-hand rule, if my magnetic field is pointing up into my south, I'm going to say that my area points that way. So I start off with a nice positive dot product. So first, right-hand rule, thumb up, finger curl. This is positive current. As this gets closer and closer, B increases. So I get a positive flux change, which means a negative current, which is how I ended up with my blue current arrow doing what it's doing right here. Once it's passed, our flux now is decreasing as this thing falls away. It's decreasing, which means negative rate change in flux with a negative sign out front in our equation, positive current, which is why the current swings around. And for a solid copper tube, I have an infinite number of these. So I have a whole bunch that are producing the same green induced magnetic field below it, and I have a whole bunch that are above it, and all of it is giving me an upward force. That is Lenz's law. Why do I get current induced? Because the magnet falls down. Lenz's law says that we will experience a force to oppose that, which means a force up. All right, so we literally just talked about this. So here in this one, if I have my magnets moving in this direction, I'm going to have an increase in my flux, right? So if I've got all these three arrows, are they connected? They are. All right. So if I swing this right here, as I do this, I'm going to get a bigger and bigger and bigger magnetic flux until I get to right here, maximum flux. And then it starts to decrease as it moves away because the field line is going to be the strongest and most condensed right next to my magnet. So I get an increase and then a decrease in my flux through this wire. So if my red field points up, I'm going to have my arrow pointing, my area vector pointing up here. So thumb up, finger curl goes in and out. So this direction of my cursor, that is the positive direction. Increase in flux, negative sign, decrease in my EMF because of the equation. I get current going this way. And if I have current going this way in blue, check out my green induced magnetic field. I have a loop of current. Take your thumb, right-hand rule for the magnetic field around a wire. I realize we were using lots of different first right-hand rule. You just have to know the difference between them. I'm finding the magnetic field around a wire. My thumb goes to the left, my finger curl goes inside, which means I get this downward pointing magnetic field. Which means this right here, I've essentially turned it into a little electromagnet. Because I've got charge flowing around, that's an electromagnet with the north end pointing out. Two norths oppose each other, so when I move this thing to the right, it's going to encounter opposition. As it gets pulled away, I'm decreasing my flux, a reversal of my current, a reversal of my green field, a reversal of my green poles, and now I have south and north attracting each other. So as I move close, I have a repulsion. As I continue past over here, I get an attraction. And either way, it is trying to stop my right-hand velocity. Okay, eddy currents. So this right here is how you would actually use a magnetic braking system. What you have is a large conductor. It's a wheel. It's a rotor. So this could be like something on your car. It is rotating around. What we have is an external magnetic field in the red region. So right here, we have a tiny little section where I have a magnetic field pointing through. And in this case, I have it pointing straight in. So as this thing is rolling along, this small section right here encounters a magnetic field. So since we can see that these particles are going to be moving to the left, if this thing is rotating around a circle, the particles here, tangential, are going to the left. So let's use our third right-hand rule to figure out the force on the positives here. Fingertips in. Motion is our thumb to the left. My palm pushes down. So our positives move down with these blue arrows. Now, as the positives move this way, there is now a void of positives. They need to get replaced. So positives actually flow in from outside the little dotted section. These charges come out, and what happens is we get this swirl or an eddy. Like in a river, we get this swirl or eddy of current. Same thing over here. So we get this current moving. Now, if I have charges that are moving down. So think about it. The red arrows and the motion of the disk cause the charge to move this way. Let's do our third right-hand rule and figure out the force felt by those charges. They move down. Our fingertips go in with the red X's, and our palm points to the right. So the charge is moving down. They move down because the field pushed, because of the motion of the disk, they get shifted downward. But that same magnetic field pushes back, I'll be done in just a second, pushes back on those same charges, giving us a force this way. You say, well, yeah, well, if I have arrows moving down, blue current moving down, getting pushed to the right, aren't these going to be pushed to the left? And the answer is no, because there's no magnetic field here. The only magnetic field is right in this region here. So if you think about it, the red arrows move the charge. So the X's. The red X's cause the charge to move. But at the same time, the red X's push on the moving charges back to the right. So motion of the charge to the left because the disk is spinning. The magnetic field pushes the charge down, and the magnetic field pushes on moving charges, so the charges that it moved, it pushes back against them. It's kind of a weird, cyclical kind of thing, but this is called magnetic braking. So how do we slow down if we're not using friction? Well, you're going to get immense amounts of heat, so your magnetic braking dissipates things through heat. I actually took a video when I was at Cedar Point with the students a long time ago of the Millennium Force. As you're getting situated and going through the corral, getting to the little gatehouse to get onto the Millennium Force, you actually walk right underneath the ending where they actually have to apply the brakes. And there's these little mechanisms that just pop out, and you say, what is that? Because all it is a metal plate zipping past a metal bracket. There is no friction. Like, what the heck's that even there for? That's the magnetic braking system of the Millennium Force. Okay. A metal detector does the same type of thing. Metal detector has that wand usually, right? So there's your wand, that little circular ring. In that ring there is a wire. That wire has current going through it. So it has its own magnetic field in red. Here's a chunk of metal. As this wand starts to come over here, what happens is this thing is going to produce an eddy current. As my field gets closer and it gets stronger, I end up with a change in the flux. So let's say this chunk of metal is my that's my conductor. It has an area. As this thing swings over, it produces an eddy current. That eddy current has its own induced magnetic field in green. And what do you have in your metal detector? You have another coil that can detect this. So you have coil 1 producing an eddy current, and coil number 2 in here that can detect external magnetic fields that were caused by our wand. And so that's where you'll get that different tone. When it comes down here, here's your bad guy trying to get knives and guns onto the plane. This day and age, no one even flies anymore. All I need is a face mask, I guess, to keep people away. I don't know. Whatever. You walk through that big, ginormous metal detector. What do you have? You got two sides to it. One side has this ginormous coil of wire, and it is producing a magnetic field. That magnetic field is going to induce eddy currents on any metallic things. Those little eddy currents are going to be detected by this sensor right here. This sensor already knows what magnetic field it should feel from this source, and any variance to that is going to cause it to ring. There's metal on this person. So that's how your metal detectors are going to function. Okay? And so what we'll do is, let's see, what do we have here? We'll do one last slide right here. Induced electric fields. We don't do a lot with this because it's just a little bit of a different kind of a concept. So what I have here is a metal core. It has a cross-sectional area A. I have a blue wire wrapped around. What I'm going to do is I am going to alter the current. I can either increase the current or decrease the current. I can't really change the area, right? So I'm going to come over here. So what I have is my flux is going to be my magnetic field, the Bunny equation, multiplied by the area, which cannot change. So that is my equation for flux. Can't change this. Can't really change the number of coils very conveniently. Can't change the area. So the only way I'm going to be able to change anything is by changing I. Changing current changes the field. Changing the field is by definition changing our flux. So what we're going to do is we're going to change our current. So as we come down here, increase our current gives us a negative induced current. So increasing primary current here, we're going to be looking at the secondary coil. The secondary coil is a separate piece of metal. We want to induce a current in it. So we end up with a primary blue current I that I have right here. And that's going to give us an induced current through here. So it's a secondary current. If we look at this right here, so there is the flux caused by our blue current. There is my cross-sectional area. We end up with a negative induced current. So take your right hand, put your thumb for area, put your thumb in the direction of the red X's. That way our positive, get a positive dot product. Our finger curl is clockwise, which means positive current is like this, and we have negative current going back this way. So right there, first right-hand rule for positive current is clockwise. We get negative current. Now here's the thing about this. Anytime charges move, you got to have an electric field. Anytime. So our magnetic field is inducing an electric field. So the work done as we go around one rotation. So we scooch down a little bit. As we go around one full rotation, we can figure out the work done, which is going to be F dot dr. In this case, we'll call it L for length. So we find that our force is going to be our charge that's being pushed multiplied by the electric field, dot dl. And so if we factor out Q, this right here, work, is energy. Energy is our, right here, is charge multiplied by our voltage. So we actually have a way to figure out our voltage through this coil by doing E dot dl. So when I come down here, we get this equation right here that shows us the EMF is going to be, if we do a surface integration, or in this case a line integral of E dot dl, it gives us that EMF. And what is interesting about this, and we don't really dig into it very much, but what is interesting is that we can have this electric field. It is non-conservative right here, non-conservative. Think about it. If you have an electric field and we were moving points around, as long as you ended up back at the same point, we used to say that it was path dependent, right? It didn't matter how we got to where we got. Think about gravity. If I'm at the 2-meter mark and I move my mass, as long as I get back to 2 meters, my total change is going to be 0. It doesn't matter what happened in between. Well, now we don't have that anymore, because now I'm going to have a charge go in one full rotation, it just got pushed by all this energy. It gets back to the same spot. Shouldn't it have the same amount? Well, no, it literally just got pushed by this positive amount of energy all the way around. If I'm at a 2-meter mark for gravity and I go up 1 meter, there's positive work being done. And then I bring it down 1 meter, negative work being done. There was never any negative work being done. It was always positive work, which means I shouldn't end up in the same spot. So what we're finding is that we have non-conservative electric fields. So there is no starting or ending point. You get this non-stop field. And what this does is we bring it all together, and this will be the last slide right here. The Maxwell equations. The Maxwell equations, he didn't actually really do much for all of these equations. It actually are equations from other people, but he put them all together. What do we recognize? Gauss's law, Ampere's law. We actually did both of those to actually calculate things. Gauss's law for magnetism. We said it doesn't really do much because it's 0. And now we have E with a line integral, which kind of matches Ampere's law. So I've got dot dA, dot dA, dot dL, dot dL, and they all have different things. What he did, and I'll find a video that you can watch if you want, it's kind of some high-level math, and sometimes it doesn't make a lot of sense the first few times. But what he did is he put all these together. This is how electromagnetic waves, aka light, travels by using these combinations, or this combination of equations. So again, we call them the Maxwell equations, even though this is Gauss, this is Ampere, this is Faraday. He's the one that put them together, and so they are typically referred to as the Maxwell equations for the propagation of electromagnetic radiation, aka light. So we'll continue talking about self and mutual inductance next week, and that should be the end of it. So this right here should get you a good start on our next online assignment, which should be number 25, and then 26 is coming right after that as well. So I'll see you at the Zoom meetings if you have any questions. Otherwise, go through the notes and bring the questions as you got them.